Okay, today on Math with Malia, we're going to cover Savvas enVision for Algebra 1, Topic 10, Lesson 5, Compressions and Stretches of Functions. These are transformation rules that we have covered with other functions, so hopefully these rules are familiar and we will deepen our understanding of how changing the function will change the graph. Here's our explore and reason. We can see three quadratic functions, g, h, and j. They all have a vertex of 0, 0 at the origin. Part A, they want us to write the quadratic function or the equation for each parabola. I'm going to start with h because it looks like it might be close to the parent function. It's the one in the middle, so let's see if we can write our equation for h of x. We're going to see what happens to the input in relation to the output. So we can see that we have this point 1, 1. So when the input is 1, my output is 1. I know that these are quadratic, so I'm squaring the input. 1 squared equals 1. So far we're fitting the parent function. Let's take a look at the other point that they've given us. 2, 4. When the input is 2, if I square the input, I do get 4. So h of x is our parent function. We can write the equation just as x squared. Let's take a look at g. How would we write the equation for g of x? We're going to do the same thing. Let's look at our points that they gave us. So they gave us this point 1, 0.25. Now when the input is 1, we would expect to be able to square it and get 1, but we didn't get that. So what do we have to do to our input after we've squared it, 1 squared? What do we have to do to 1 squared to get 0.25? Well, we have to divide it by 4. So we can write times 1/4 or times 0.25, either one would work. Okay, let's look at j, our last function. So again, let's take a look at the point 1, 4. Looking at functions that all have the same input. I know that if my input is 1, I should square it and get 1. So what do I have to do to 1 squared to get an output of 4? Well, I have to multiply it by 4. So there we can see what the function rules are for each of these graphs. So how are these functions similar? Well, they're all parabolas. We can see that. They have the U shape. They all intersect at the origin. They all have the vertex at the origin. They are all upward facing. How are they different? Well, they're either stretched or compressed. Okay, the width or the narrowness of the function is different. Okay, using your knowledge of compressions and stretches of other functions, what would we do to write a vertical stretch of the square root function? Well, we would do the same thing. We would just need to have a coefficient in front of the quadratic term. So we could multiply it by 2, and that would be a vertical stretch. Or we can multiply it by 1/2, and we would get a vertical compression. Example 1, analyzing reflections across the x-axis. How does multiplying the output by -1, so if we have a -1 as our leading coefficient for our quadratic function rule, how does that change the graph? So here's our first function, our quadratic function. We see our two parabolas, and when we have a -1 as our leading coefficient in g of x, we can see that it is reflected over the x-axis. Okay, so we just have that line of symmetry there on the x-axis. And so our parabola is downward facing. For the cube root function, don't get confused. It might look like you've reflected over the y-axis, but really we are still reflecting over the x-axis. So this part that is increasing on function f then reflects over the x-axis and then becomes the decreasing part. So again, anytime you have a negative leading coefficient, then you will be reflecting across the x-axis. Write a function with a graph that is the reflection of the graph of f across the x-axis. So again, we just went over this rule. Anytime we are reflecting over the x-axis, that means we are multiplying by -1. There needs to be a negative leading coefficient. So we can write different things. You can have any value as long as it's negative. So you could even say -2x, or just -x, -1x. And this works as well for the square root function. As long as your leading coefficient is negative, it will be a reflection across the x-axis. So you can have different values in there for the coefficient as long as it's negative. Example 2, analyzing vertical stretches of graphs. So remember, vertical stretching, we are stretching along the y-axis. We're changing the outputs. Okay, so we should see a coefficient outside of the parentheses, or a coefficient multiplied by the whole function, by the whole output, not just the input. Okay. Now, when our coefficient is greater than 1, what does that do? Well, let's look at the graph where the values for the input are the same. So if I'm looking right here, I'm going to zoom in. If I'm looking where the input is 1, for f of x, my output is at 1. But for g of x, my output is at 2. So after I square my function, what did I have to do to get an output of 2? Well, we have to multiply by 2. So vertical stretches make the function narrower. Okay, we're stretching it vertically, so it's going to make the parabola narrower. And the output is going to be farther away from the x-axis. All right, let's take a look at the cube root function. So again, focusing on where the input values are the same. So right here, with an input value of 1. For f of x, when x is 1, my output is 1. And for g of x, when my input is 1, my output is 4. So I'm taking the cube root of my input. The cube root of 1 is 1. So what would I have to do to 1 to turn it into an output of 4? Well, that's where we are multiplying by 4. We're taking the whole output and multiplying it by 4, so it's increasing or it's being pulled farther away from the x-axis. So that's vertical stretching. So just remember, anytime k, the constant you are multiplying to the whole function outside the parentheses, anytime it's greater than 1, it is a vertical stretch. You're moving away from the x-axis. Example 2, try it. Write a function with a graph that is a vertical stretch. If we are stretching vertically, we are stretching along the y-axis. We are changing the output. So anytime we are changing the output and we want to stretch it, remember our constant needs to be greater than 1. So any value for the leading coefficient of the function that is greater than 1 would make it a vertical stretch. So you could say 12x, 3x, any value for k that is greater than 1. Same with the square root function. As long as that coefficient that is on the outside of the function is greater than 1, it will be a vertical stretch. Okay, example 3, vertical compressions of graphs. So remember, with compressions, we're going to be changing the input, okay? Example 3, analyzing vertical compressions of graphs. We're still changing the output. Since we are talking about a vertical transformation, we're changing along the y-axis. So we will be multiplying a constant on the outside of the parentheses, or multiplying it on the whole function. But now our constant is going to be a fraction. It's in between 0 and 1. So looking at the absolute value function, again, where the inputs are the same value, let's compare. For f of x, when the input is 1, the output is 2, okay? We can see we've shifted it to the left 1 because of that plus 1 inside the parentheses. So we've talked about that in a previous lesson. But how is the output changing? For g of x, when the input is 1, the output is 1. So what did we do to get our input to go from 2, to get our output to go from 2 to 1? The input is the same. We take the absolute value of 1, and then what did we have to do? Well, to get 2 to 1, we have to multiply by 1/2 or divide by 2. So we're taking the whole function and dividing it or making it smaller, so the output is going to be less, and we are moving closer to the x-axis. That's a vertical compression. This works for quadratic functions as well. Let's take a look at our two parabolas where the input values are the same. Okay, where x is 1, for f of x, our output is 1. And for g of x, when our input is 1, it looks like our output will be 1/2. So what did I do to my output to go from 1 to 1/2? Well, again, we are dividing it by 2, or multiplying the whole function by 1/2. Multiplying the whole output by 1/2. Vertical compression gets us closer to the x-axis. We're smushing the graph down towards the x-axis. All right, let's try it. Write a different function that is a vertical compression. So again, our constant that we're multiplying on the outside of the whole function, our leading coefficient needs to be between 0 and 1. It needs to be a fraction. So any value can work for a. Any value that is a fraction. So it could be 1/3 the square root of x. It could be 1/16 the square root of x. Anything smaller than 1. Still needs to be positive because we're not doing a reflection. Okay, for part B, same thing. As long as the constant is in between 0 and 1. Okay, example 4, analyzing horizontal stretches. So remember, anytime we're changing a function horizontally, we are changing the input. We're moving along the x-axis. Okay, so that means we are multiplying something to the input. We are changing the function inside the parentheses. So we're changing the input. Our constant will be on the inside of the parentheses. Okay, so they gave us a table with values of f of x and g of x, and let's take a look at the graph. When the outputs are the same, since we're changing the inputs, I want to compare where the outputs are the same. So for f of x, this looks like our parent function. It's quadratic, it's parabola, so when the input is 2, if I square 2, I get 4. Okay, and for g of x, in order to get an output of 4 with an input of 4, I have to change the input because 4 squared does not get me 4. What squared gives me 4? Well, 2 squared gives me 4. So in order to change my input, I have to multiply by 1/2 or divide the input by 2. That will get us the same output of 4. So you can see we are moving the input. We're moving the input away from the y-axis. Okay, so this is a horizontal stretch. We're pulling it horizontally. It's like if you take both ends of the parabola and you're pulling it away from each other. We're stretching it out along the x-axis. Okay, so why is g of x, 0.2x plus 2, a horizontal stretch? Well, we can see that we have a constant multiplied by the input. We're only changing the input. You could, in a sense, put invisible parentheses around the 0.2 times x because I'm not multiplying the whole function. I'm not multiplying the plus 2 by this constant as well. So since it's only changing the input and not the whole function, this is a horizontal stretch. The change is happening inside the parentheses, the change is happening to the input, and so I am stretching the input and moving it farther away from the y-axis. Example 5, analyzing horizontal compressions. So remember, anytime we're doing horizontal translations, you want to think opposite, or horizontal transformations. Any type of horizontal change, you want to be thinking opposite. Okay, it's going to go the opposite direction than what you think. So horizontal compressions, again, we're changing the input, multiplying by a constant. So we're multiplying the constant inside the parentheses. But now our constant is going to be greater than 1. So let's see what happens with our parabola. Again, since the input is changing, I'm going to look where the outputs are the same. Yeah, I don't like that one. That's going to be too weird. Let's do this output. Okay, for f of x, when f is -2, my output is +1. Okay, and if we plug that into our function rule, -2 plus 1 is -1, -1 squared is +1, so that works. For g of x, when my input was -1, we got the output of 1. So I have to change the input to have the same output. What did I do to go from -2 to -1? Well, in order to get g of x to match up with f of x, I have to multiply it by 2. So in order to get g of x to match up with the parent function, or with the original function, I have to multiply the input by 2. Okay, so we're changing the input, and again, this time, instead of going away from the y-axis, we're actually moving closer to the y-axis. I'm going from an input of -2 to an input of -1. Okay, so that's why it's opposite than what you would think. Even though the constant is +2, we're not actually doubling. We're saying in order to get g of x to match up, we have to multiply it by 2. So again, if I go from g of x to f of x, I do multiply by 2. Okay, so that means we have to do the opposite. To go from f of x to g of x, I'm multiplying by 1/2. Okay, and that's what I did here, 1 and 2 for our coefficients. So any change to the input of our function, when the constant is greater than 1, it will be a compression. We're smushing it horizontally. We're moving the inputs closer to the y-axis. Okay, let's take a look at the absolute value function. Again, looking where the outputs are the same. Okay. So here for f of x, when my input is 2, my output is 3. For g of x, it's an input of 1 that gives me an output of 3. So what do I do to 2 to get to an output of 1? Well, we're dividing it by 2. That means if I go in the opposite direction to g of x, I have to double the input in order to get the output, or I have to double the input to get me the same output for f of x. Okay, so that's what this is saying. Take the original input and double it, and that will give you the same output. Okay, and we can see that when we start with f of x and then we move to g of x, we are going closer to the y-axis, so we are compressing. We're taking both sides of the v and squishing them together, a horizontal compression. Just a good rule of thumb, anytime you're having a change inside the parentheses, think opposite, okay? Just like this is a translation to the left 1 unit, then anything that is multiplied will also be the opposite. Instead of being a stretch, it will be a compression if the constant is greater than 1. Okay, I hope this is making sense. Again, we've done these transformation rules before with other functions. Okay, we're on our last try it for the lesson. Write a function with a graph that is a horizontal compression of the function f. So remember, horizontal compressions, we're changing inside the parentheses, changing only the input values, and in order for it to be compression, you've got to think backwards, so our constant needs to be greater than 1. Normally, we think of compressions when it's vertical. We compress it by making it smaller, but since we're changing the input, we have to do the opposite and actually make the input bigger. Okay, so any value for our constant that is inside the parentheses or the radicals, you can think of those as a special type of parentheses. So we're only changing the input, any value of a coefficient or a constant that is greater than 1. And for part B, again, same thing. We're changing just the input. So I'm changing inside the parentheses. Notice what I did. I like to add parentheses because I'm squaring the 2 and the x. Okay, that's different than 2x squared. Okay, without parentheses, this would be a vertical stretch because only the input is squared. So this time we did have to add parentheses to show that we were changing the input, and the whole input would be squared. All right, you made it to the concept summary for stretches and compressions of functions.